last session. Go ahead, please, Lou.
Okay, here we go. Let me get up a board to write on. There we go. Now let me see here. All right. Are there questions from where we were before?
So far, not yet, I guess.
Okay. So let me begin today by talking about knots, the mathematical approach to studying knots, and then we'll make it a little more general. But let me just talk about the mathematical combinatorial matter of knots and links. So we have this phenomenon of I like black for this. We have this phenomenon of things that can be knotted, and you could have a knot on a rope like this, and I could model it by a picture like this. So if I wanted to study how this knot behaves, I could take this picture and fool around with the picture and see how it behaves. So, and what I mean by fooling around with the picture is, suppose, for example, that I had drawn a very similar picture like this one. And these two pictures are obviously exactly the same, except for right here, right? Right here, this one goes over, weaves over, and here this just weaves under. But if your eye is trained in the way most of our eyes are trained to look at pictures of this kind as though they were little bits of rope floating around, I mean the same training that leads you to interpret this guy here as a cube in space. It's that same convention of picture examination that we learned without any instruction when we were children. In this society, you interpret that as a cube. You see this; these are the edges forward, and those are the edges backward. And the basic convention is that of crossing of edges, which is understood that this is closer to you. The eye, your eye, and this is farther away. That is the convention that we are imbued with. And so I can use that convention, that pictorial diagrammatic convention, and I see this, and then I see, oh, well, then this could be changed a little bit into this without going across the ends or anything, just staying in the middle here. And then this could be pulled a little bit tighter, and it would come out like that, and it got unknotted. And on the other hand, I can't do anything to this in the same way. I can't get rid of it. Now, what I like to do to analyze this is to close the ends so that I don't have to ever worry about sliding something off the end. So I look at knots in a closed piece of rope. But I don't always do that. Sometimes I have the ends out there, but then I have to always be careful not to slide something over the end. I'll show you what I mean by sliding something over the end by doing it. This is an example of what I'm forbidden to do, but let me do it anyway. Let's see, there we go. I've drawn everything except this part here, right? And I could take this part here and I could slide it all the way out there and bring it back. But I say no, all right? I'm not going to allow myself to slide the rope off the end of the rope. if we were examining a knot together for some practical reason or otherwise, we might tie it on the rope, but we are not going to slide it off the end, because you can get rid of anybody by sliding him off the end. So if you close it, then that effectively eliminates this possibility. And here you are with this knot on a closed loop of rope. And is it knotted? How do you know? You probably believe that this one's knotted, but how do you make a mathematical model?
Does it matter for the number, even number or order number of those crossovers?
Just one moment. I'm trying to write what I was saying, and then I take it's a little slow. How do I make a mathematical model in which we could prove that T here, trefoil knot, T is not equivalent to an unknotted circle? Okay, that's the I want to show you how I can make a mathematical model, just like you can prove in Euclidean geometry that something has a certain property. But now, getting back to this, you started to look at it and conjecture things about it, like odd and even, right? This has an odd number of crossings in it. And this one has an odd number of crossings in it also, but they're arranged differently. So, Jason, did you want to say something more about what you were thinking?
No, I was just guessing the number of the order or even of those crossings might matter.
Well, it might. So you might think, well, maybe you have to have an odd number of crossings in order for something to be knotted, but that is not so. Let me give you an example. This is called this has a few of the early knots have names. This is called the figure 8 knot. And it has 1, 2, 3, 4 crossings. Do you notice anything else about it would be easy to make the figure 8 knot unknotted also by switching or crossing. Here, what I did was I switched a crossing. Here's this crossing, C, and here's this other crossing, C prime, and I just operated on the crossing to change it. It's not a topological operation, but it could cause unknotting. I could switch a crossing like that, switch. So I'll call that S for switch, crossing switch. Now this actually happens in biology. That's a key point. That this could be a bit of DNA and it's knotted, and it's not good for the DNA to be knotted, because if it's knotted and it reproduces itself as DNA does, then the two new DNAs would be linked up with one another. And that would be very bad because they have to separate into their individual cells. So it turns out that off in biology, nature has enzymes which will, there's an enzyme which will come along and break this, open it up. So after the enzyme is acted, this is much farther apart. It isn't broken here. It just looks broken for our visual convention, right? It really goes continuously across, but the enzyme cuts it. The enzyme is still there, and the other arc is still there, and it allows this arc to move downward a little bit, the other DNA arc, and then the enzyme puts it back together again. I probably should draw the enzyme as kind of around the whole thing, and puts it back together again in such a way that it's going over rather than under. So that line, did I draw it the same? Yeah, there's always that problem in drawing.
Lou, would you like to entertain an objection and perhaps a contradiction to your
Well,
line
wait,
of
wait.
reasoning?
Let me finish. Let me finish my description here. Right, I could
Okay.
show you better pictures, but the idea is such a simple one, and I wanted to stay with my blackboard. What happens in biology, and Yang and his collaborators at Harvard really verified this for the first time back around 1978, that there are enzymes, and those enzymes will take a bit of long chain molecule and they will cut it. And then you have an opening, and another long chain can slip through the opening, and then it puts it back together. And of course, that has the effect of so this was a switch operation, and the enzyme can do switch operations, and as you can see from this example, it's quite possible, and we'll see that it's true, that you can unknot anything by some switching operations. Now, what was your? So I just wanted to bring to your attention the notion of a switching operation, and that you could think about unknotting other things than this truffle knot. You could unknot the figure-8 knot. Actually, any crossing switch at all on the figure-8 knot will undo it, won't it? If you tried it. Suppose you decided to switch. I'm talking a little bit, but I'll let you talk in a moment. Let's suppose I switch that crossing, and then it would look like this. I've kept everything the same except that one place. But now this also pulls apart. You see, I could just relax it a little bit and it would come apart like that. And then these curls would go away. And so this is unknotted. So this is unknotted after the switch. But if I don't allow switching, and I wouldn't normally, you can't with a rope unless you cut it and recut and reconstitute it to do a switch. Your rope will remain knotted. So this is a situation where you can think of doing certain operations that can make something unknotted. That's the end of my long sentence. So now, what were you going to say?
Yeah. Okay. So I think there is a linguistic problem here. And my response is nothing to do with the geometry that you illustrate in terms of lines and that sort of thing. Rather, mine is a linguistic issue with regard to the nature of the language of biology or language of DNA and its
Okay,
composition.
go ahead. Now, let me make a remark quickly. I use the word nature and that something happens in nature. And I mean that the way any other scientists would be talking. If we're going to get involved in cyber speak, then we have to put reality, we have to put objectivity in parentheses and all sorts of things that we like to do. And maybe you're going to bring that up. Go ahead.
Well, you're on the edge of where I was going, on the edge, but not really where I was going. There
Yeah,
is
go
this
ahead.
problem. There is this problem with the notion of the physics of atoms, and the physics of atoms is such that if you join two of them together, you get a molecule. But that
I'm
sort
going to
of thing,
take notes on you over here in this little box so that we can come back to it. I keep talking. You don't have
okay,
to do understand. I'm just taking notes. Atoms, molecules. Go ahead. Go ahead.
okay. Now, a atom, it consists of two types or two forms of particles. We can call these logical particles. They are separate and distinct logical particles.
Well, wait. I mean, atoms are said to, at the level of my sixth grade, when I was in school, atoms consisted of protons and electrons,
And
nuclei,
well,
and electrons. And then we later learned about other particles. So there's a nucleus of one charge, and there are electrons which are going around the atom with another charge, right? That's the usual description. What are you talking about? I happen to like the word logical particle, but that's something else again. Go ahead.
well, no, label those as being distinctive objects. So one, if you want to label those as plus and minus, that's fine with me. So if you want to look, electrons is minus and the nucleus is plus. But the
Yeah.
point is that they're separate and distinct objects.
That's the way we usually describe it before we begin to have to think about quantum theory and the change in the notion of object.
Well, that's how I'm choosing to use the language. That, for example, in the notion of electricity.
Well, but I do have to point out to you immediately that once we start studying quantum theory, the electrons become electron clouds and so on. And the notion of what is the individual nature of the object is reconsidered in relation to the structure of the mathematical models we use, Schrodinger equation.
Yes, yes, I agree totally with that. Okay, that once you make that transition from a rational description of a molecule, or excuse me, an atom, as consisting of two types of parts, that's the limits of my logical particles. The motion of those logical particles, if you want to describe that in a mathematical model, then I assume you would use quantum theory or some other, if you would, assumptions or presuppositions that inject motion into your line of thought. So
Sure.
I'm not thinking of
Sure,
those.
and we know about all those different strategies. You call them logical particles. It's very interesting. That means that what you're thinking of is they have certain rules associated with them.
Exactly.
And we know
Now,
some amazing things, right? Like radiation can go along, and then, ooh, this can happen in the cloud chamber. And over here you get an electron, and over here you get a positron, right? And all kinds of weird stuff goes on. And we would like to think of this as one kind of particle becomes another kind of particle.
But you're switching the language. You're adding additional definitions and presuppositions into your explanation.
Yeah, as you said,
your interpretation.
Right. As you said, you want to think about dynamics for them, how they move, and so on.
Well, you're adding more to your language and your mindset that you want to use to interpret my language and my mindset. I want to keep.
So you haven't added any dynamics yet. You're just calling them logical particles.
Exactly.
But I have to interrogate you, of course, to find out. Do your particles have location?
Yes, they have location. They're separate and distinct from all other particles.
Do they have momentum?
I haven't said anything about motion. I'm just logical particles.
But your logical particles have location.
They have location.
Does that mean that you have a space in which you can talk about things being located, or is it relative?
They are relative. They're relatives in space. That is, there's a relationship between them.
Are you assuming there is a space?
Yes.
A space that can be described by coordinates? That's a lot of things to assume.
Well, it requires multiple coordinates, but that's another issue.
And then the next interrogation is, why are you concentrating on this when we were talking about abstracting the properties of rope in space? I think it was because I started talking about DNA, and DNA is understood to be made out of molecules in our modeling. I got to molecules because I was talking about molecular biology for a moment, and the idea that the long chain molecules could be knotted up with one another, and there is the question of how you would know that a long chain of molecules was knotted. That's very interesting. How do those biologists know that the DNA could be knotted? But they did know within the framework of the knowledge that they have that the DNA could be knotted.
Lou, I understand your descriptions. I understand the biology. I'm a biochemist. I've done a lot of work with enzymes over my career.
You, right, exactly, you.
Yes.
But we're talking,
exactly,
we have to here, listen to me. This is procedure.
It's methodology.
No, you listen to me. This is procedure. We have
Go
to
ahead.
talk in such a way that we're sharing our definitions with everyone else.
Exactly.
Jamie raised the hand.
And I can, and I have the right to say to you, I'm going to talk about some results in molecular biology, and I will speak in the usual well-known language of biology that you would read in a magazine article. And if you then want to go into the epistemology of that or the foundations of that, we could, but we can go on forever into that depth.
No, we cannot go on forever into that depth. We can only go as far as the language permits us.
Yes, that's
clear
correct.
distinction.
So
What I'm saying is that there's a clear distinction between
look, I
your
don't want to get
definition.
into an argument with you.
I'm
But
not arguing.
you have your ways of speaking, and if
Jamie,
you
your
want
question.
to, I'm going to clear this board, and I'm going to work with you for another 5 or 6 minutes on what it is you're trying to tell us. Now, let me just clear the board first. I have to say that.
Save the image,
There's
please.
one sentence. If I can get to one sentence, it'll clear the entire argument.
You don't understand. I'm doing this procedurally. Give me time to clear the board so you don't talk over that while I do it, because I'll get confused.
Oh, okay, I wanted to maybe, as I was listening to Jerry and Lou, I think, Jerry, that
I've asked people to stop talking while I do this silly thing, because otherwise I get confused.
okay, I'll
So
wait with
that
my
means stop
comment.
talking.
Wait, Lou, finish this job.
Just let me do this.
We'll get to the same point. Let them do it.
Yeah, saved.
Okay. Now,
Well, it's a great name.
so we have atoms and we have molecules. And we have logical particles.
Right.
And we have space. And we have location.
Correct.
And we might indicate the particles by their sign, possibly. Yeah. Okay, so far so good. Keep going.
Well, we actually don't need anything more than what you have, or we don't even need that much. The only distinction that I wish to make is that logical particles, as named by the notion of an electron and a nucleus or whatever, okay, are distinct, discrete objects. They are not continuous in any mathematical sense.
By your definition.
No, by the nature of the way nature is organized.
Oh, I'm sorry. You have an objective nature, which you have your own personal knowledge about. How nice.
No, it's
Pardon
not
me for being sarcastic.
It's science of chemistry. It's a science of chemistry.
No,
if you want an example, use a Nernst equation.
Where do you know about discrete objects?
Discrete objects? Well, Avogadro's number is one place to start.
Ah, you have evidence of discrete objects.
Yeah, Avogadro's number.
Oh, tell us about Avogadro's number. We don't
all
know
another
chemistry.
discrete
Well, wait.
Okay.
Avogadro's number. Tell us what it is.
It is a collection of objects that end up to give the a number that is an atomic number equivalence in its mass. So that if you have the atomic number 1, then the
Do you
number
teach chemistry?
1 gam. Pardon?
Do you teach chemistry?
Do I teach chemistry? Well, I have taught chemically related subjects, yes.
So what do you tell your class when you tell them
Um,
about Avogadro's number?
I usually I don't need to talk about it in any definitive
Look,
sense.
look, you haven't told us what it is. I've asked you to give us the elementary explanation of what is Avogadro's number.
Well, you want to introduce the concept of mass and collections, and I don't want to go that far. All right. I just want to make the simple distinction that a discrete particle is part of the language of chemistry.
Oh, yeah, it's certainly part of the language of chemistry. And let me make a remark. Chemists came to understand that things were composed of what apparently were certain numbers of discrete particles because of the ratios of measurements, right?
Yes.
You can't see the molecules, but you get
Yes.
evidence that in a given amount of material, there are a certain number of molecules because of
Yes.
multiples of things.
Yes.
Right. So you don't, so those discrete objects are inferred. Molecules are inferred discrete objects for the chemist. They aren't seen like
Yes,
the
they're
pen.
inferred. They're
This
inferred
pen,
from atoms.
this pencil is a discrete object in my space, and we can look at the boundaries of it, and we can say it's here and it's not over there.
Yes, I'm thinking more in terms of the symbolization of how we approach the objects of the world. And the way that we approach the objects of the world in our symbol systems, in the atomic table of elements, is a sequence of numbers, 1, 2, 3, 4,
Yeah.
5, etc.
That's
These
right.
are discrete
That's right. But where
these are
you
discrete symbolic objects.
but you have to admit that the molecules and the atoms are inferred discrete objects for the chemist, whereas the the notion of discrete object is coming to you out of your immediate world.
Well, the notion of a molecule is by the addition of two or more atoms. So that if you have the number 7 and you have
and that's your model because you've never seen them.
Well,
They're
I haven't
inferred.
seen them.
They are inferred.
Well, I can infer, if you want to infer them, then I can infer them, for example, in the view of chemistry. Now, not my personal view, but
right,
in the view of chemistry,
why should we have an argument over this? Molecules and atoms
because it's critical. It's critical to the logic of what you're going to say. That's why we should argue about it.
Well, I'm almost ready to quit.
Okay, but if you
Because
want one example of a single
insist
molecule,
on taking over. Listen to me. I don't like it.
okay, I'll stop.
I don't like it.
No further questions. I'll stop.
If you want to argue, you're going to have to be very careful and explain your terms, and you don't do that.
Chemistry.
And I find it very annoying.
Yeah. Well, Lou,
and you could leave, or I could leave.
Okay.
Okay,
let's stop immediately.
Let's hear.
And I'd be perfectly happy if you simply left. But if you want to talk, you're going to have to be much more listening than you are.
Let's hear Jamie's question. You raised the hand for a long time.
Do you want to ask a question about this?
Actually, sorry.
Huh? You're muted.
I did not want to ask a question. I just wanted to give a clarifying comment that, but I don't know whether it's necessary or relevant. That Jerry is really talking like a chemist and he's not understanding mathematics, I guess. But I maybe shouldn't say anything more because the whole point is Lou is trying to explain or share his know-how, and that's why I'm here. So I'm going to stop.
All right.
Okay, Lou, please continue your original agenda.
If we were, yeah, never mind. The point is that when you're doing science, you do make reference to lots of existent things. and you speak of them as though they existed, just like the objects on your desk. But when you look at it, you understand that you've never seen them. They exist because they explain things for you, and there are lots of evidence for it. That's fine. But I haven't gotten to I haven't understood why you wanted to correct the language here. Yeah, I just don't
Maybe-
understand what point Jerry is trying to make. I'm sorry
Okay,
to have
okay.
gotten angry, but
That's okay, and
um,
I
But-
can perhaps clarify a little bit. Like Jerry is very much thinking like a chemist, and he's investing a lot of energy in coming up with an arithmetic that is grounded in the atomic table. But
that's all fine and good, but just a
Yeah.
moment. Let me show you a picture. We were talking about molecules. I'm looking for a picture. Let me see. That'll do. Look at that.
So he cut you off.
shower.
Can you see
Yeah,
that?
I think there might be difficult for people to connect the concept of nodes in terms of a line or connections.
We'll get
Well,
back
with
there.
the
Yeah, but
discrete,
please, I do want one more thing, one more item to show you. Right.
Howard.
Right. There are various kinds of, I'm sorry, I have to put the earphones back in. Now, what I'm showing you here, I think I better stop sharing for a moment. All right, let's go back. We're talking about knots. And there are places where we're talking about defining knots, and there are places where we're talking about knots that occur in your own reality, right? And I don't have to talk about molecules, although a chemist understands that the rope is made of molecules, but it's a rope. It's a rope. And I'm referring to your experience. And I'm referring to your experience in the fact that I can tie a knot in the rope. So then the question is, do you have any difficulty with that? You may or may not have as much of the experience of consciously tying knots in the rope, but you tie knots in your shoelaces, right? You're actually an expert at tying certain knots, as is everyone who lives in this society with shoes. So you already know a lot about knots, and you may or may not have done the slightly more abstract thing of tying a knot in a rope like this. But when you tie a knot in a rope like this and you take a picture of it like this, the picture looks just like the kind of picture I was drawing. So I'm taking this and I'm making a sketch of it. When I make the sketch of it, it looks like this. And as I said to you, this sketching is very simple, but it's something that you may not have much experience with making sketches of this kind, and I would recommend that you do in order to understand them, because it's complicated, but very simple at the same time. The key thing about making sketches of this kind is that you have a line that's broken and another line that's not broken, and that you draw one over the other like this, and you thereby get a sketch. And it might be a closed loop, just as I can take a knot and tie the ends together and make a closed loop. So far, that's all I've done in terms of this kind of diagramming. Now, Jason was just saying, oh, people may be confused about that part, but are you, other than that? Yeah,
no,
go ahead.
I mean, you already from a single discrete particles coming into lines, and this you actually jumped up to a micro level. I mean, it's not it's not any. We are not talking about molecules or particles anymore. We're
No,
talking,
no, I'm not talking about molecules here.
yeah.
But I'm saying that, but I started to say that DNA biologists realized that the DNA could be knotted.
Yes, go ahead, please.
And how the heck did they get to that? How did they get to that? Pardon me while I clear the board over here so that I could scribble on it. Now, what you're looking at, this thing here is an electron micrograph, an electron microscope photograph. So they know that the DNA is made of molecules, but you can't see the individual molecules here. All you see, in fact, you don't see the DNA here. What you see is an image of DNA that's been coated by protein to make it thick and heavy and visible to the electron microscope. And then they see this. And then they say, it looks to me like a picture of a knot. I could make the schematic sketch. And then I get over here to this one, and I think it looks like it's going under. See? You have to look carefully. Is it going under or over? Which way did it happen? And then this one, and then under here, and back to where it started. And that's my sketch of this electron microscope photograph. So I abstracted the information in the electron microscope photograph, interpreting these parts of the photograph as crossings. And probably this got into the paper by Cosarelli and Spengler back in the 1980s, because those people agreed, after looking at it carefully, that the weaving of the DNA must have been as I drew it over here on the right, alternating weaving. But they have to know a lot of different things in order to actually have a correct inference here. They have to know a lot about how the proteins are that coded the DNA work. They have to know that that these molecules are really lying over and under one another when they cross, and they have to agree that this photograph is sufficiently good to be regarded as evidence, because this is something from the very small and inferred through the electron microscope. But that's how people learned, how people came to believe that DNA could be knotted.
Yeah.
And of course, it's not the only evidence either. There's chromatography and other things. Yeah.
One question. If you were to take this picture and rotate it 90 degrees,
yeah,
take it to a plane perpendicular to what we are looking at.
Oh, you mean if you rotated it so that you were looking at it edge on?
Yeah.
Mm-hmm.
I'm assuming this is not a two-dimensional structure; it's a three-dimensional structure.
Well, right, but these things got flattened into some planes in order to take the micrograph. The electron micrograph demands that things be put on. You know, it's similar to using an ordinary microscope where you had to put something on a flat.
No, well, where I'm totally lost is this a knot, or is this because we are taking a 3D picture in a 2D plane?
Yeah, we can see clear the
I thi-
overlap.
that's a nice question. Let me try to address it with a computer demo.
Okay. Th-
Um, whoa, let's see what happens here. Sorry. I thought this was working. I changed computers the other day. It probably works. Yeah, but I don't know why this. Hmm. Ah. Ah. All right, that's working, but I wanted to be able to just input things like I normally do, and I'm on a different computer than I usually use, so I'm sorry. I hadn't checked this out.
So it is unfolding.
All right, that's working. But all right, so this will do here. This is this is yeah. Um let me sorry, I have to get from that will do. That's a good file. Mhm. All right.
It return.
All right. So here is something that if you yeah, this is fine. I'm just not happy with this extra junk that's going on here. I don't know why I can't get rid of it, but we could see this. Here's a projection of a 3D object, and I can move it around, right? And I get different projections of the same 3D object. They should all represent, they should all, they're all these, each of these could be regarded as a diagram like the ones I'm drawing because they're happening in the plane. And that goes under and then it goes over and over and then it goes under and so on. But if I rotate it around in space, like you were saying, what if I rotated that around in space? I get many different diagrams. And you might think that this is knotted. It kind of looks knotted, right?
Yeah.
It looks knotted, but it isn't. Um, and we're going to see that it isn't if I let this program run. What the program does is that it coats the knot with mathematical charge and self-repels it. So that means that a point here on the knot and a point here on the knot are going to experience a push away from one another like an electrical force. And every pair of points on it do that. Now, there aren't an infinite number of points. We get to the discrete objects matter in the modeling, because what's really happening is that there are these points, okay? The knot is actually these points, one after the other, going around like this. And it isn't even this strut in between. The computer graphics draws this. As far as the program is concerned, it's just handling these points, but it's going to handle them in such a way that this strut here is never going to pass through this strut here. So it moves it around like a piece of rope would move around. And then the graphics can hide that and just show you a smooth thing. But what will happen if it self-repels? Watch. Now let's stop it. You're seeing that it's unknotted now.
Yeah.
But still, if you had it drawn this way, you might think it was knotted, but if you rotated it, it would become more and more apparent in some of the ways of looking at it that it wasn't knotted. Like you could pull this under here. Or what if you rotated it by 90 degrees and looked at it this way? Well, then it's a little harder to see. So I really thought it would be a good idea to take your question about what if I rotated it and bring us into that more fully, and we can let it continue. And of course, it will unknot further because it's pushing away from itself.
So it'll become a circle or a loop, right?
Yeah.
So you mentioned there exist enzymes that can, in case it cannot be, in case it is knotted, then it will cut them off and reconnect them. And that process is very interesting, I think.
Now the process, but this guy was unknotted to begin with. But let's go back and look at him again, right? There he is again, and it's still not so easy for us to see that this is unknotted. It's some steps away. It's like trying to look at a chess game and see that there's a checkmate and it's to be done in 4 moves. So it's not so easy to see that this is actually not knotted at all. Right? So we have that's part of the problem from the point of view of understanding a mathematical model for such a thing. The other thing is just to, maybe you'd like to see it happen again. Okay, so that would continue, and it's becoming a non. Now there's a good example of here it's crossing through itself, but if you took a different point of view and rotated it, then the amount of crossing through would be down to just one crossing rather than many. And this movement is one that I was drawing in the plane by thinking of pulling it a little bit, right? So so this is a part of the situation. And let's look at another example of that. suppose that I take this rope and I tie an ordinary knot in it like that. And then I make the knot a little more complicated. Maybe I did this last time. It's a magic trick, but it's also illustrating what we're doing. It's not sleight of hand. Now I've made a more complicated weaving there, right? And now I make it even more complicated, say, by dropping it down through the lower loop like that. This is still knotted, believe me. I'm not kidding you. But then remarkably, if I then thread it through the top here, then I arrive at something that kind of looks knotted. And you would have to be a genius of visualization to see exactly how it comes unknotted. But if I pull on it, it does come unknotted. So you see, I do have a problem here that a mathematician could try to get their hands on, which is, how do I tell when I have one of these things in front of me whether or not it's knotted or it isn't knotted? And how does the DNA get knotted is a correspondingly interesting problem, which I'm jumping over to for a moment, because you could start, the point is you can start with things that are not knotted, like this closed loop. Imagine that's a closed loop of DNA. And the DNA can twist in its environment, so it might twist around itself like this. And then another pair of parts of it come together and it could twist around like that. And then it could twist around some more in its environment, maybe like that. And you end up with something like this. Which looks knotted. It's not knotted. You know it's not knotted because you just saw me make it out of something, and you could just go backwards along the line by which I made it. I didn't cut anything, and there it is. But on the other hand, it looks knotted. And one thing that could happen is that one of those enzymes could come along and break it and put it back together right there, for example. And if it did that, then the whole thing could become knotted in a complex way. And that kind of thing does happen. So it turns out that those enzymes, which can switch crossings, are really important for the biology. They're what keep the biology from just getting all ensnarled. Now, I wanted to share screen again. As long as we're playing with the program, I want to show you how one can go dynamically. Let's see, sketch. Oh my, let's see, reset. Undo. This, I have to do something to obtain my own autonomy with this program. Let's see, delete all. That's good. There we are. All right. So we're actually are in the position to draw. So I can make drawings like this, see? And if I don't do anything and I come back to where I started, it'll go under. But if I press shift on my computer, it goes over and then under. And you see, I just made a knot. That one's going to be a knot. And then you can say done. Finish. There. And then I can go back to the main part of the program. And I now have this guy. He's flat. He's like, I got drawn in a plane, but there he is. And we can let the program work on him, which self-repels it and makes it more three-dimensional. See? So just because it's in the plane doesn't mean that that it would unfold into something unknotted when it goes out of the plane. It might unfold perfectly well into something that not only is knotted but has some interesting shape. In this case, like that, uh, and so we can go back here and sketch whatever we like. Let's just do one more or less randomly here. So I make whatever I want. Um, and then in the world of drawing, I can make all sorts of things like this, and they're flat. And when you look at them on edge, they don't show very much. But the program lets you explore something that would be very difficult to explore any other way. You let it self-repel, and it starts to become a three-dimensional entity. And you can make it with smooth tubes if you like, and you can do something, which I'll explain what I'm doing in a moment. I'll just let it do it. Kind of letting it move around a little more freely. And you end up from the diagram, from the abstract diagram of the knot, getting something which is a good deal more three-dimensional and has some properties that have to do with the self-repulsion, of course, like the fact that when this goes through this loop, it goes sort of in the center of the loop because it's being pushed away by all the points along the loop itself. What happened there was that in the program, there's a spring force in here of an artificial spring force that lets these points move back and forth that way, as well as self-repelling. And when I turned this on, the spring force is happening. And so these will be moving back and forth a little bit this way as well as self-repelling, and it looks more dynamic. So this leads to problems that we have no idea how to solve mathematically. All sorts of problems, because you see, the flat diagram of the knot goes into this three-dimensionality and repulsion, and you get these three-dimensional geometric forms, and we don't know how to classify the geometric forms at all. It would be difficult to predict what will happen when you take a flat and you turn it into a three-dimensional form. Very difficult to predict. Maybe I can show you that experiment, one experiment about that as well. I'm not sure that's the one I want. Oh, it might be, but we'll try it anyway. Here's a flat. And what will happen to it if I ask it to self-repel and turn into a three-dimensional animal? I might have gotten the wrong one, but we'll see. Yeah, this is a good example. You see, you couldn't have so easily predicted that it would start to do what it did. And it ended up in this quite different form from what had happened, what happened when we just drew it in the plane. So we understand very much that when we draw these figures in the plane, we're missing all this geometry. And in fact, we don't know how to handle the mathematics of this geometry except by, for the most part, except by a computer simulation. So that's part of the situation. Okay, comments or questions on that before I go back to the blackboard?
So how does this relate it with the self-organization of the structures and
Oh, it's worth pointing something out about that. Let's go back up here. Oh, I go through this again. Maybe I just talk about it. When you looked at, oh, I'm not careful, I'll punch the leave meeting button instead. Yeah. When 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 you have any of these gadgets, any of them at all, this one was the DNA, and consider what would have happened if we could, for example, a nice experiment for us. We should do it, but I'll do it next time after I figure out how to control that program a little better. But suppose that we were to take this, which was the DNA, and this is the way it came in the electron micrograph, and then we could hand it to the program and it would open it up into a three-dimensional structure, and you could wonder whether that 3D structure was, it sounds like I'm not answering your question, but I think I will be in a moment. The thing is that when you take the knot and you make it into an independent entity by plugging it into itself at its ends, so that you then allow it to move, but you're allowing it to move under the constraints, then it is self-organizing within those constraints into some entity that is repelled from itself, right? But it isn't self-organizing in the sense the question you're raising is about self-organization. And one way in which we can think about that is related to what we were talking about is within given constraints. Within given constraints. So in this case, you were given something, you drew it, and then you said, all right, this is not allowed. But other movements are allowed. For example, in my drawing space, the following movements would be allowed. I would be allowed to change the diagram like this, like that, or like this. Those happen to be important to me, and I'll explain why, but they are just different ways in which you could you could deform it. These preserve the topological type. It's still the same knotting of the rope, but these are just things you could do with rope in space. Then under those allowed movements, the topological organization is preserved. So that's the thing that we're talking about from the point of view of the knot theory. If you allowed this to move around a bit, you could, let's use this one. I mean, I might, for example, take this guy and I might push him underneath himself right there like that, right? And he's still the same knot. The organization of the knot is preserved, but the appearance of it has changed a lot. So this is that. But on the other hand, there is the other aspect of self-organization, which is emergence. Right? So how would it not emerge and then become stable? So you could imagine a story which was something like this, that you had something that was unknotted and maybe it curled up a little bit like that, and then maybe it wandered through itself like that, and then maybe it even ended up binding to itself at the ends. And by the time it bound to itself at the ends, it would have emerged as a knot that was going to be organized, self-organized, and stable for some time after that. But then you would need to have a story in which that could occur, right? So does that begin to answer the question about self-organization?
Mhm.
Um,
Snakes biting the nails.
I'm sorry, say it again.
I mean, the snail biting its own nail,
Oh yeah, so
eating.
right. So if you think of this, which could fall off the end, as a snake which could bite its own tail, and if it could bite its own tail, why then it would get locked in, and it would be stable. And that's exactly the reason why we would do it. If we wanted to examine the knot, we would splice the end of it together so we could pick it up and move it around, and it remains organized. Okay, so let me continue with this.
Lou, I have a question. When your computer program is running and is trying to unravel the shape, there must be some criteria that you're using to get the algorithm the unraveling algorithm.
Oh, yeah,
what is
exactly.
a fundamental concept in that?
So what is happening in the computer program is that if you have any 2 points, these are 2 of the beads.
Right.
Then these beads are experiencing a force this way and this way, radially between them. And it is, in the case of the computer program, there is a distance between these, and the force is equal to some constant times 1 over the distance to, I could use the 5th power rather than the 2nd power to get a better result in the program, but you can adjust that. So it's like a 1 over r squared repulsion force. So then you have your knot. Let me draw a knot. You have your knot, which is really the sequence of 3D locations, some finite number. And then for every pair that you see, except adjacent pairs, you don't deal with adjacent pairs. That would result in some problem, but a non-adjacent pair will experience a force. So they'll be pushed apart. And the program can check to see that that in the course of its movement of these things, it doesn't cause a crossing to switch. No crossing switch.
I'm sorry, I didn't understand that. Can you explain that again? Sorry, I didn't know. I don't understand what you mean by no crossing switch.
Well, it's possible that you might. I try to draw it in a specific instance. You might have a situation like that. And
Right.
maybe this bead, for whatever reason, wants to move up. Right?
Okay.
But if it moves up too far, then you would end up in the following situation. It just sent this bead up, but it caused these two lines to
Right.
change, and
Okay.
and now it's unknotted. So this would be checked for it. You would check that if this should happen, if you went from here to here, I would say no, right? So this bead wants to move.
Yeah.
But then I check the location of it afterwards and before, and I check that these two lines
okay.
are now in the
Yeah.
other position. So that's some calculation that the computer has to do to make sure that nobody crosses anybody else.
Okay. A string cannot cut another portion of the string. That's what you're saying.
And that's right. It can't switch across.
They can't cut. Okay.
Yeah.
Okay.
So
that means that as you see it move in the program, it's staying within those bounds. But of course, it can get in trouble. It can get stuck, for example. That's one of the ways in which it can get in trouble. It can try to move, and it ends up like as though one bit of strut is touching the other bit of strut, and it can't get any farther.
Yeah.
There are various ways in which it can go wrong. Yeah, that computer program, it will go wrong.
Lou, does this assume that the bond between the two adjacent dot between the two adjacent dots is very much stronger than that expelling forces you use it to untie itself?
Wait, I didn't quite understand the question. Say it again. The bond.
I mean, there are two forces working on here. One is the one represented by your line. So it's the boundary, it's the attachment between the two dots. And that force must be way stronger than that expelling expanding
you're,
forces
I
between the
understand.
stars.
I did tell you that there is a spring force here.
Ah,
In the program with, so these 2 points can move back and forth by a spring force. But that isn't actually necessary. You could write the program without it. You could also ask, well, what about the distances? Well, the distances between the points is also allowed to vary, but if you let it vary too much, the whole thing would just go out into space. It would get larger and larger. So the program has some constraint on either the total. I'd have to look inside the program. I didn't write it. Rob Sherine wrote it. He either has a constraint on the total length of these distances, or a bound on the distance between 2 points. It can't get bigger than a certain amount. Because otherwise, if it was just self-repelling and you didn't put some bound on it, it would just get bigger and bigger, right? You could start with 3 points that are nearby one another, and they're self-repelling, so they would get farther apart, and then they would get even farther apart, and so on, like that, right?
Look at this. These are all magnetics. They sort of bonding together. So have you tried to experiment the same knotting or unknotting experiment with materials like this instead of a rope? I mean, this is more like
well, this is imaginary material in the program, right? But of course, you can think about how easily or quickly do things unknot, depending on the materials out of which they're made, right? Like the metal rope I showed you a moment ago is.
yeah, that was very strong, but
this metal.
this is not very,
You were holding up something. I didn't see it because
I'm holding up this magnetic string.
magnetic. Yeah,
Yeah.
magnetic string, right?
They kind of bonded by their own forces. So if the whole knot thing, if you use this kind of maybe something more round, like a little balls, magnetic balls, then would the same thing happen? I mean, I'm talking about the
let
forces.
me get another demo. I'll be right back.
Okay, we're talking about the differences of these forces.
Yeah. So even though we are talking about a continuous rope, but when you're trying to model it, you have to discretize it into nodes, right? And then assign a certain force, a relationship between those, imagine a relationship. So you have to enforce, you have to deduce a continuity between the observed nodes.
Because he was talking about the DNA, and I think the
The
boundary between the molecules can sort of be modeled by the boundary of these magnetics.
Yeah, but what I understood Lou to be doing is he is being mathematical, so he gives an abstract model.
So you were playing with
applied in reality.
I'm sorry.
Go ahead. Sorry. Yeah.
You were playing with magnets.
Lou, it's Lisa. Can you just let Margareta finish her point?
Go ahead.
Thank you.
Okay. I was just pointing out is that Lou is talking as a mathematician, at least that is the way I hear him, giving an abstract structure, a model, like there's a universal language to talk about knots, but it's in the as a model, imaginary space, so to say, and then we can apply it, and then the word observe comes in. So, like for instance, with the case of the DNA, but when you go to the real world, then of course there is a whole bunch of additional assumptions that comes in, and I think that's what Jason is doing, bringing in a magnetic force,
Sure.
and so then I'll give the word to Jason.
All right, Jason, you were using magnets. I wanted to show you another conceivability. These are poppet beads. So these beads fit into one another. Can you see? Sorry, maybe you can't see.
Yeah, we can see.
Yeah. Yeah.
They fit into one another like that. So I could tie a knot in the poppet bead and close the end. Now I have a closed loop knot. And this is good up to a point, but if I start pulling on the poppet beads hard, they'll come apart, right? So now my constraints are, these are not bad. They stay fairly well, but if I start putting forces on this, it will pop apart because it just like the magnets will come apart.
Yeah.
And on the other hand, this I can demonstrate with this what I was saying about the DNA, because here's an unknotted collection of molecules, if you like, bonded together, and they twist around one another, and they twist around one another a bit, like this, and then somewhere along the line, this is unknotted, but there it is. So there it is, and somewhere along the line, one of those enzymes comes along. And it
So what is the word you're using? I don't.
Enzyme.
Enzyme.
Oh, enzyme. Oh, sorry.
Enzyme.
Okay. Enzyme.
One of those topological enzymes comes along.
Yeah.
You can see when I'm out here, and it breaks and one of the bonds already broke just spontaneously. Like I said, you have to be careful about that. I'm going to do it again. So this twisted around itself a bit. And then one of the enzymes comes along and it breaks the bond and slips it through and reconstitutes it. And whoa, now we have a knot, right? So the DNA became knotted as a result. And conversely, somehow or other, the DNA is going to become unknotted by the enzymes acting on it and managing to unknot it. Of course, I can do that here. I can say an enzyme acted right there, and it put it back together, and now it's unknotted, and so those kind of operations are happening in the reality of the molecules,
yeah,
by our inference.
Yeah. Well, the whole DNA duplication requires the strand to be unraveled, right? Yeah.
Right. You need the DNA. The DNA becomes two strands rather than one strand when it duplicates. And if you had two strands that were wound around one another, they wouldn't be able to pull apart, and the cell couldn't divide. So Wang and his collaborators saved the day. It took a long time for people to discover that that was really happening. Remember, it was in the 1950s that the DNA became accepted as a process. And it wasn't until the late 1970s that there was evidence for how the topology was being solved.
Yeah.
Yes.
But yeah, go ahead.
I was going to add that the DNA is actually like it behaves, like you say, the topology in the cell, it behaves much more dynamically and weirdly that many people conceive, because they think of DNA as, you just have the chromosomes and that's it. But actually they open up and they interact with the DNA of other chromosomes. So when when it's being transcribed, that there are actually pieces from multiple different chromosomes that are aligned and that are being transcribed together. So there is,
Yeah. So there's all kinds of things that are going on other than the
yeah,
topology, right? The DNA chain itself is it can be regarded as a chain of characters, of codons, of information, and that information is being transcribed and retranscribed,
but
and all of that going on.
Lou, but I wanted to emphasize the topology of DNA, actually, that it is very crucial to understand, because that people just
Yeah.
think there is not, that it isn't changing, that people think, oh, that's irrelevant to understanding how it functions, but the more we understand it, it becomes very relevant.
Yeah, and more as people understand more about it, but there are many mysteries there.
Yeah.
Sure. Let's go back now and talk about the model. As Margaretha was saying, I'm working between talking about how we make an abstract model and how those models could be used. Let's get another Blackboard. So the abstract model that I'm using is one that a lot of us use, and it looks like just just diagrams for a while, but the diagrams are highly useful because they are faithful to making the constructions. So I'm using diagrams that are based on having a crossing like that, and then I can draw things like this that represent different knots. And these are like sketches that you can make, but they are actually quite precise sketches within topological bounds. I mean, I could draw this, or I could draw this, and they're the same as far as I'm concerned. The topologist doesn't care about moving, contracting it, moving it. I could have this this part here all wiggly, but I can smooth it out afterwards. I can reduce this like this. So this is just like I could take a rope and I could put a knot in it. And if I take the rope and you can you see what I'm doing as well as my screen when I'm here, or do I have to stop sharing? Do you see me holding a knot?
Yeah.
You do? Oh, okay. Somewhere off on the side you do. But if I take this knot and I splice the ends of it together so that it won't fall off the ends, then I can do all sorts of things to make this bigger, right? I could pull it out like that, or I could twist it around itself a few times and slide it through itself, and it becomes a much more complicated thing. And I can do the same thing to these diagrams if I want to. I could take this diagram and make it into something even more complicated by deciding to move this underneath this, and that doesn't change it topologically at all. And then I could take this part here, and I could decide to move it over this part over here. I can play with these diagrams like that, and this still hasn't changed anything. It's still the same knot. So I have this infinity of different forms of it that can occur in the diagrams, but the diagrams are all just graphs in the plane, four-valent vertex with some structure at the vertex, either this way or this way. And so they're well-defined mathematically up to their topological type, and you can play with them as diagrams and see what happens. So so that's the model. The model is these graphs, but then how are you allowed to move them and we have allowed moves, and the allowed moves come from are the ones that I drew on the other slide. You're allowed to take a twist and remove it. You're allowed to have somebody going underneath somebody else and pull it apart or put it back together like that. And you're allowed, if somebody goes underneath here, then this could be pulled downward without changing everything outside it, so that it goes underneath here like that. And it turns out that that can be the rules for the model. There's a theorem that I'll just say these are the rules of the game. Okay.
Hello, it's Lisa.
Yeah.
I just, I want to back up for a second to that top right corner of this sketch board. Because I want to go to a very basic shape, and that is the lemniscate, the 8 on its side. So you have one point of crossing. And the reason I ask, I'd love to know about that shape, starting with just that. So can you tell me, describe that for me as what's happening?
Well,
Equals 0.
sure. Now you assure me, but I'm always a little skeptical that you see me well. If I do this, what's happening? Oh,
Well, we can slide.
I'm sorry.
There's a divider. Yeah, we can slide.
I'm
So-
sorry.
No, we can see.
I'm sorry. I'm having a. Oh, I see what happened. That's what happened. Yeah.
So if we slide
just
that
a
little bar.
technicality. Okay, there. Now,
Okay.
because you see me full bore this way
Yes,
around.
now.
Yeah. So here's your lemniscate.
Mhm.
So in the three-dimensionality of it, you have a circle, 0, and you go to infinity, if you like, by giving it a twist, right? Here's your lemniscate. You could have done it this way, or you could have done it this way,
Mhm.
right? I could do it more than that. I could do 2 of them or 3 of them, and I'm twisting up like this, right? If I try to do more than that, it'll break in this case. But you like this shape, this infinity sign shape in 3 dimensions that comes out here.
Yeah.
But what more are you thinking about in relation to it?
I'll tell you why. Because that I'm curious about that particular shape for a number of reasons. One is it's an ancient symbol.
Mm.
It represents, like you said, infinity. And when I do some of the modeling that I do in the sensing into highest future potential for a systems map, I tap into sensing geometries. And this is a shape that I have sensed a number of times, and it's one that I can feel in the body. So again, I'm always playing with this sense of the observer in a larger field, which goes.
I have a couple of comments about that at this level. Let me try, okay? I didn't want to stop you. I just wanted to get back to my blackboard so I could. There. We're gonna keep this slide, but I want a new one. No? Yeah, I do. so I want to concentrate on this relationship. And if I labeled this line A and I labeled this line B, just to give it names, Alice and Bob if you want, or something, then I'm going to say that A is in the membership relation with B. A is in a hierarchy with B. B is over A, all right? And if we were to switch the crossing, then it goes the other way. This is still B, and this is still A, but now B is a member of A rather than A being a member of B.
It's
And
just
then
a
if we,
definition or it's,
that's just the definition.
okay.
When you say definition, are you saying description? What's the difference?
Well, I'm just describing that
Mhm.
there's a relationship between over and under. So we can think of this as membership if we like.
Yeah, I hear you, but I'm just questioning Jason's question is in
This
this.
is just a definitional, but the point is that it is part of the diagrammatic that these are in asymmetric relationship to one another, right?
Mhm. Yeah.
You can say that A is beneath B or that B is beneath A, right?
Yes.
So we could have a little observer out here and he can travel along and then he becomes another observer in here, or we could have two observers, but this could be the same observer. Well, let's call this one O and this observer O prime, right? And O is observing that O prime is inside and O prime is observing that O is outside above him. But because of the lemniscate, they can go one to another. He can become, he is the, or you could say that B observes A, okay? If you want. So O is observing O prime, but O can be, but O prime can walk along the lemniscate. It's like those Escher drawings where you go from in a lower part to an upper part and back. So he walks along and he ends up here. And he keeps on walking. And he ends up back down here, right? So the observer is the observed, if you like. Here you're up here. I've got too many little figures here, so I'll circle them. The two that I had in mind. There's O up here, and there's O prime down here, and they look like they're distinct, but they're actually, their roles can interchange. O can walk along the lemniscape and come down here, or he can keep on walking and come back up there. So there is the twist allows that that multiplicity of roles to occur. So that's part of the structure of the lemniscate.
Yeah, and I
I'm sorry. Let me say one more thing. So,
Mhm.
oh no, let me hear what you were going to say.
No, please. I'm curious.
All right. So what I would do with this, if I think of it as membership, what happened? Yeah. If I think of this as membership rather than this, then we could say that this is like emptiness. There's nothing in there, nothing going underneath it. But this one, and this one, we have, this one has no members, but this one has a member. And so this would be like a set containing an empty set.
Oh, Lou, we're back to Kate and Joe.
But let me make it a little more interesting. Suppose that I had a link. Then I'll write down the members of each one, right? I can write down the members by looking at who goes under. So B goes under A so that the member of A is B. but A goes under B. So the member of B is A. And so these sets are linked with one another. A is a set whose member is B, and B is a set whose member is A. A and B are pointing to one another mutually. And that mutual pointing to one another can be indicated by linking. And so we could think of the mutuality of A and B as corresponding to topological linking if we think along the lines of this. And then this, your lemniscate, is somebody that's a member of itself. Let's call it omega. And then you see that omega has as its own member itself. So it is a set which is a member of itself.
I'm
So
not,
self-reference
yeah,
and the lemniscate are directly related to one another.
okay, so there's two things on my mind right now. The first, when you drew the set, the single set, the empty set, and then the two lines crossing, the arcs on the lower right, you know, that was a shape I remembered from the children's book that Stafford Beer wrote for Kate.
Mm-hmm.
And so that's interesting. But now we have a linked set. So what the reason I look at the lemniscate, I feel that we are often noticing the endpoints and not these other points along it.
But the lemniscate has no endpoints, right? It just goes around.
Right, but
But in the smooth going around, the roles can change. On the one hand, there is the lemniscate as container up here, container or observer, and
where are
there
you
is the
on slide?
lemniscate as the contained down here.
I'm not seeing your pointer right now.
Oh, if it draws, that's too bad.
Oh, maybe just tell me where you're looking.
There must be a way to make this into a pointer. Maybe
Yeah.
you see this pointer. You see
Yeah.
this pointer?
Does
No,
anybody see? Oh, no, that's my pointer.
You don't see a little pointer here?
no.
No. There should be a way to point. Well, of course, I can always draw. So I'll point by drawing. Let me erase our observer up here.
Okay, now we see where you are.
And let me erase one of the observers down here. And then let me replace him by omega. And down here by omega, because it's all omega. The whole thing is omega, right?
Mhm.
Omega is the name of the entire lemniscate. But omega up here is the container. And omega down here is the contained.
Yeah, interesting.
And the container is equal to the contained.
Too bad people don't know that.
So your lemniscate is self-reference, self-pointing.
Yeah. Very interesting.
Another diagram for this. But this one is interesting because there's a continuity. There's a continuity of going between being the container and being the contained.
You're pointing to, you're describing the circle right now? that you
Oh,
just
I'm
drew?
sorry. It's too bad that pointer really doesn't work. There's no way. But I'll just use another, sorry. I don't want to draw too much is the point, but let's use another color anyway. There's a continuity between being the container and then you travel along. And after a while, you're the contained. And then you can become the container again. So they're the container, you're the contained, you're the container, you're the contained. I am the food, I am the eater, I am the food, I am the eater. You see this again and again.
Hmm. Yeah. Well, again,
So
yeah.
if a simple circle were an oscillation, there's no change going on. But if we were to put into the single circle an inverter so that here it's marked, but then when it goes through the inverter, it becomes unmarked. But then when it goes through the inverter, it becomes marked and it becomes unmarked and it becomes marked and it becomes unmarked. It's the same
Wow.
pattern, the same pattern. But this one is showing you how you could have sets that are members of themselves and it's perfectly all right. They're topological. And you can have sets that are mutually members of each other and it's all right. It's topological.
So have we just gone from a circle to a spiral?
So we have gone to a spiral in the sense that this spirals up once. We spiraled up once.
Where are you now? Sorry.
We spiraled up once like that, right?
Mm-hmm.
Here's the circle down here, but up here we spiraled up once. And then for the lemniscate, we came back down to where we started. Here's your lemniscate folded inward on itself, right?
Mm-hmm.
So, but of course we could spiral a number of times if we wanted to,
Mm-hmm.
and then come back to where we started, or we could spiral without limit.
And does that describe a DNA helix?
So that feels like a DNA helix, doesn't it?
It sure does.
So what you make of that depends on where you are sitting in the train of ideas or the metaphysics that you have in mind, right?
Well, I get stuck into
but down here is just the pure circularity coming right back to where you started, and above it is the pure spiraling.
You're in the upper left now of the
Up a pure spiraling up here, pure circle down there.
Yeah. Okay. Yeah,
So-
very helpful. Thank you.
So how about mutation, Lou? What happened when mutation happens? Is that your little over in the relationship of crossing getting broken?
Well, if we're going to talk about mutation in the biological sense, then you were looking at the DNA as a chain of molecules, right? And of course linked with another chain of molecules and the bonding between them and the fact that it is a DNA spiral, and some external situation causes something to change in here, right? Like a cosmic ray comes in and knocks the molecules around. So it has to do with the fact that the information in here in the DNA molecule is has to do with the sequencing of the codons in the molecule, and that can change, and it can get re-recorded in a different way. So then we're going beyond the kind of topological model that I'm using, where I don't know anything about the internal structure of the lines which I'm working with, right? When I draw a knot or a linkage, I don't I don't know anything about how they are composed at the outset anyway. And it would be more complex to try to understand how it would behave if it was made of particular things. On the other hand, when we did the computer programming, we had to make it out of something. So we made it out of beads. And the computer program, if it were going to be a little more molecular, could have a whole string of different types of beads for having information, and then it could have mutation and other things could go on. Interesting, right? But I don't know how the question you raise is one that I don't know much about, right? You're saying how is topology of molecules related to mutation?
I would like
But
to
yeah,
maybe reverse the question is how is mutation better understood by understanding topology?
well, yeah, read the question backwards. How is mutation related to topology?
And
Either way.
what do we mean by mutation? Because we just think of a switching of a molecule, but it's not just a switching. There is
It's
also
what
a
influence did
topological
it have?
change.
What influence did it have? By some mutation, maybe we could become smarter or more empathic, or maybe it's just going to change the color of my hair, right?
Or that because of the topological place where it takes place, that it doesn't make a difference, or that it may that we need to think differently about the mutation. It's not just a replacement of a
Yeah.
molecule.
Now,
It's also
in this case, I think it's a really important question. Sorry, I interrupted you. Important question. If we were to go to the internet and look through the research papers, I bet we would find that some people are actually trying to understand something that's like that.
Yeah.
Here's something that is a little like that. Excuse me, I have to find my.
Margareta, could
Oh.
you finish your sentence so I can
Yeah,
follow?
please finish.
Oh, we can't hear you just yet.
You're muted.
Yeah, okay. We used it. We in the conversation the word mutation was used as if we know exactly. Okay, this is what it means. There is a change in from an A to a T or a G to a C, but that actually by putting it in the topological the context of a conversation about topology. That it is not just about the sequence. So the way that people think, we have sequenced the genome. Now we do know how DNA works. We have access to everything we need to know about DNA. But that there is also the question of how it's located, or the topological structure of the DNA, and so that we actually don't know very little so far. En dat, dus wat een mutation, a mutation means a change.
Yeah.
And instead of just thinking it's a change in a molecule, like with all this, just that how can I say, you send a little bit DNA and then they say you're likely to get breast cancer, but no, it's the DNA doesn't tell anything about the topology. So maybe there is zero likelihood of getting breast cancer because there is something else that we're not looking at that we should be looking at. So that was where I was going.
Yeah, so you might have a widened notion of mutation where maybe there would be some combination of molecular and topological change.
Yeah.
And an example that's analogous to that is recombination.
I'm
In
just,
molecular biology, there is a process that the enzymes do that's called recombination. And in recombination, you have, do you see this marker?
yes,
That's interesting. So you see that marker because it's a PDF file. All right. You see this marker. And what happens here is you have this supposed to be one DNA, but and you'll notice that this one is topologically just an unknotted circle. You untwist it. But if you were to cut this apart, let me show you the operation. This is recombination. In recombination, you have, sorry, you have a couple of lines of DNA like this. And what happens is that the enzyme cuts out these bits here and it reconnects it this way. So you start with this, and this is the in between, and then afterwards it's reconnected like that, so that if you started A here and you were going to B here, and this was C and you were going to D, then here you'd be A and you would end up going over to D, and here you'd be C and you'd go into D, so that the chains of connection among the molecules have been changed by the recombination. And there are enzymes that do that. That's part of the processes that go on. I don't know any more about how that affects things, but this is not mutation, but it is change of molecular structure. And then the question is, topologically, what happens when you do that? Because you could connect A to D and you could connect C to D this way, but you could also do it the other way, right? You could switch it this way, or for that matter,
Lou, I
you
think there
could,
need to be B's.
what?
You have a B
Yes.
and a D in the original, and then at the
Oh,
end,
A,
Yeah.
B, sorry, B, B. Thank you. So what I'm saying is originally you got from A to B, but after it got cut and rejoined, you went from A to D and you went from C to B. And this would also do that, but topologically it's different. This is over and that's under. Or you might have done it this way, A to D and C to B. And now you had an even more complicated twist in here. So which of these is actually happening when the recombination occurs? So people were wondering because they can't see it. They can't see it directly. But what they can see are the results. Sorry. So here, this is a schema of it. You see, I started with this, and I did a recombination, and I did it in the specific way, over, left, over, right, like that. And I did it again, left, over, right, and then I did it again, and then I did it again in my diagrams. And you can see that you get topological products of a certain kind. Started with unknots, then you got these simple links, then you got these figure 8 knots, and you got something else and something else. If the recombination was happening this way, then this is what you would see in the electron microscope. So they tried experiments like this. They actually set up experiments where they could make it recombine successively like this. They don't know that it's going to be over rather than under, or twisted once rather than twisted 3 times. And they do the experiment. And in the experiment, they find out that they're getting a preponderance of these links and these knots, and maybe even that guy with a lemnis gate with somebody linking it, right? And so that is strong evidence that the recombination happens topologically this way. If you had done it the other way, we could draw pictures of this. So you could draw this over instead of under, and you get different links. You could try it yourself. Suppose you take this diagram, take a screenshot of this, and then try drawing it the other way where this one goes over, and you get a different entity altogether. So you get a spectrum of topological things coming out that you can see by means of the electron micrograph, and those experiments were done, and people are still doing experiments of this kind to try to find out what goes on in there by indirect means that way. But what I don't know is but I could find out for you, and you could find out what goes on with recombination. What do people know about the reason for recombination occurring in molecular biology, and what does it do with the information? It's analogous to what you were asking about mutation. Comment?
Okay, you have one more session to review.
So that's a place
secret.
to stop.
Yeah.
What we didn't get to today, but that's perfectly all right. Sorry, trying to move something.
Once again, we
Never
can-
mind. I'll just come back.
once again,
yeah.
we can only guess what Gerard is thinking.
The things I was wondering about, but to some extent I have the answer. What is the variety of the modeling system given the variety of the model system? It was mentioned.
So you're asking how flexible is the modeling system that we're using?
Yes. Yeah, that was what I.
Well, actually, that's very interesting to me. The modeling system that I started with, the purely diagrammatic one that only knows about topology, looks like it's highly specialized. But our attitude is we start with the topology, and we can do a lot with it because it's very simple.
Yeah.
But then if we want to do more complex modeling, we can add structure to the model. So the very abstract model, the one that only is thinking about topology and has as its basis these simple drawings, is actually very flexible indeed because you can add to it.
Yes, that was what I was thinking about. Thank you. Yeah.
And you'll notice that you can also add to it or think about it in other ways. We were talking about self-reference or sets that are members in themselves, and the same diagrams can participate there. And that leads you to think about, well, could we or should we think about self-referential systems in a topological way? Maybe that's useful. I think it's helpful to think that way, that we have that also has to do with variety or flexibility, in that we go from the linguistic level to a level of thought or reference or mind, which is maybe more topological, maybe more flexible. Maybe it can project back out in lots of different ways of language than the way of language that you bring in. I listen to you or I speak, but then the thought, whatever that means, can be re-expressed in many different ways. So it's analogous to a topological entity, like the three-dimensional entities that we were looking at, that can be projected in many different ways, and they all, in their form, represent the same less articulated substance.
That is, well, to my mind, that is an experimental procedure. You find out certain aspects that you wish to translate into the modeling system, and then you check whether you can do it. Isn't that the case?
Always, yeah.
Yeah.
Whether it's the experiment that you do with a electron microscope or the experiment you do with your ways of thought. You try out a way of thought and see what it does.
Yes. No, that's fascinating.
Jerry.
So I think
Jerry, please come out. We want to hear your concluding remarks, comments. Oh, but Jerry, are you there? Yes, please.
Yeah, it's as I started out this conversation, now Lou is going to get really pissed off here at me again because he is unwilling to listen to the distinction between discrete mathematics and continuous mathematics.
I'm willing to listen.
I've said all I need to say if he really understood what I meant.
Okay.
But let me
Well, but
continue.
Jerry, let me say
continue
something.
one
Let
step
me just
further.
say, I
Well,
really
please,
appreciate.
Please let me finish.
I'm sorry.
Now I'm getting pissed off. All right.
Go on.
Okay.
Please,
So-
go ahead.
So the issue is the question of the atomic numbers as physical objects and discrete items versus continuous mathematics as a geometric concept that is derived from the notion of axioms in geometry. These are very distinct languages of description of nature. Very distinctive language of descriptions of nature. And when you attempt to take anything to do with molecular biology and describe it in continuous terms, you are then using a different language. If you want to call that language topology, that's fine with me. You can use any language you chose to fit your beliefs to. And that's perfectly fine with me, except that there are constraints on the mathematics that are then being ignored when you use continuous functions to describe discrete chemical processes. And so the DNA molecule, I can look at it as a continuity, as a continuous sequence of, if you would, a polymer. Now, not as a molecule, but as a polymer composed of atoms, and that there is always a space between the parts of the atom. And this space is discontinuous. And that's all I was trying to say, that there's a discontinuity between the parts of atoms.
Okay.
And I perfectly think this is a reasonable way to look at the world. And the mathematics of it is quite different. And particularly the notion of the distribution and commutativity are different within chemical mathematics. So the mathematics of chemistry is just fundamentally, profoundly different from the mathematics of geometry. That's all I'm trying to say.
Okay. Because we passed the time already 10 minutes, we will let Lou address this issue in our next session. But Jamie had raised the hand. You have another burning question?
No,
I have to leave.
it was the same comment I was going to make earlier, this about the discontinuity, but I'll just wait till the next week. What I see, it's okay. Let me say this way. I'm writing a paper, it may take a while, in which I say that Heinz von Förster made a tragic mistake when he talked about the observer as opposed to a distinction drawing being. So when he came up with these two laws in response to Maturana, instead of saying an observer, if we had used the word distinction drawing, then we would have paid attention to distinctions. So what I heard Jerry say is, he says we're describing the world. No, we're not describing the world. We're developing a model. I think Lou was showing us how mathematics can be used to develop models and look at regularities in a disciplined, systematic way, and then go back to reality. And I think that Jerry somehow missed that, but maybe I'm wrong.
I want to make one last remark, and that is, if you think about the different mathematics we talked about, some of it uses continuity, and some of it is quite discrete. The diagrams are quite discrete. However, when we work with discrete things in that way, we also are working with notions of continuity in that we know how we keep it together. This is close to that. This is put together with that. This is joined to that. So notions of continuity are not just notions of infinity. They are notions of whether something is related to something else and how it is related to something else in our understandings. And so mathematics is always a dialogue between the continuous and the discrete. It goes on, and it's very deep and a beautiful dialogue. So you can think of mathematics itself as the philosophical investigation of the continuous and the discrete.
Okay, looking forward to the next session. That will be on 29th, right? 29th?
22nd.
Ah,
Is it?
But our next meeting is the 29th.
29th. So it's not next week, it's next week. Okay, please remember coming
No,
back.
wait. That's 22nd, right?
I think
Well,
it's,
Next
wait
week
a
is
minute.
15th.
It's the 30th, isn't it? Or is it
No.
the 29th? No, we meet on a Wednesday.
29th, 29th.
29th.
No, next week
Yeah.
is 15th, right?
Yeah,
Jason, you'll email us, okay?
yeah.
But
yeah,
we're
of course. There's
missing
always a
two-
reminder.
Yeah,
Okay.
We're
thank you.
missing
Yes.
we're missing 2 weeks because of my
Oh, okay.
schedules. Yeah.
Oh,
Yeah.
okay.
So long,
Okay.
thank you.
Thank you very much.
Thank
See
you,
you next
everyone.
time. I
Thank
will
you.
try to get Jerry.